Hello, in this video we're going to try to solve this problem about the Green's theorem. So what we're trying to do is to apply the Green's theorem to a plane flow that showed that the rate of the flow out of a region S equals the integral over S of the divergence of the flow. So we have a region S that's surrounded by a curve C that goes counterclockwise. We have a flow through this region S, so that we call it F. So we want to, for a given vector field F xy, let's be defined as F of xy g x y. So what we want to prove that the rate of flow out of region S is equal to the integral over S over the divergence of the flow. What's the divergence of F? It's the div F, the divergence of F is equal to the gradients vector times F, which is df xy dx plus dg e y xy. This is the divergence of F. From this, what we want to prove is the flow, the rate of flow out of region S is equal to the integral over S of the divergence of F, A, which is equal to the integral over S of df dx plus df dy xy. That's what we want to prove. To determine the rate of flow out of S, which is the amount of substance that flows out of S at a given time. So let F be the velocity of the substance at xy. So we're gonna momentarily concentrate on one point of C. This is the C, and we're gonna concentrate here, and this arrow F here, delta S, this would be the normal on the surface at the normal N. So this arrow represents the amount of substance that the substance flows out of S, the region S. In order to prove this, we're going to need the equation, the area equation for the parallelogram. So we know the parallelogram that we have, for example, with sides A and the base B. We have the height H, that's the area, would be the base times the height H. But if we have this angle theta here at the corner of this parallelogram, so we're gonna have that the sinus of theta is equal to A of is H over A. What it means is H is equal to A sinus theta. If we substitute that in the equation of the area A here, it's going to give us, is the area is B times A sinus theta. And we can see this from this triangle. So from here we have this parallelogram that's made of the side delta S and the norm of F, and we have this angle phi that's made with the normal vector n and this side of the parallelogram. So, and similarly, like we did with this parallelogram here, with the side A and B and this angle theta, we're gonna do the same with this parallelogram. A would be delta S and B would be F, the distance of the just one F, and we have the angle theta, which means that the area is gonna be delta S times the normal F times sine theta.